will study about 2:1 MUX Verilog code. Now let us look at the outcomes of this particular lecture, what all things we want out of this lecture, as in what all things we should know after the completion of this lecture. So first we will start with the multiplexers. We will learn about what are multiplexers. Followed by this, we will understand a 2:1 MUX block diagram, its truth table, and the Boolean expression, and how all of these three things are majorly very important for any digital circuit to be known, so that once you know all of this, you can very easily create a Verilog code out of this circuit that you want to create. Followed by this, we will study the uses of multiplexer. That means once we know what are multiplexers and what are all these constituents that are used to describe a multiplexer, we will understand why do we need multiplexers as circuits and what is its use in digital electronics. Followed by this, we will try to write the Verilog code with all the necessary knowledge that we have gained about multiplexers before this. Let us now look at the introduction to a multiplexer and try to understand what a multiplexer actually is. So, a multiplexer is a combinational circuit that selects binary information from one of many input lines and directs it to an output line, much like a data selector. That means this is a combinational circuit. That means it does not involve any timing elements. And what is its functionality? Its functionality is that just like a data selector, it selects binary information from many of the input lines and it directs it to an output line similar to a data selector. Right, so let us look at the diagram and understand how it works. So we have A and B as the inputs and we have Y as the outputs, and whatever binary information is present at A and B, the select line selects which input will provide the binary information to the output, and hence by that we get a valid output in Y, right? And the entire circuitry works when enable is held high, because enable helps in enabling the circuit functioning in totality. Now, if we want to look at this diagram with respect to the Verilog code that we are trying to write, so for that, always when you begin to write a Verilog code, you will need to look at this diagram as a black box, and we just need to only focus on the inputs and the outputs which will act as ports in the circuit, and whatever happens inside this black box, that means the functionality as to how this MUX will select one of the input lines via S and will produce a binary information at Y. That process and how that is being done is hidden by us at the moment in the beginning of writing the Verilog code, and for that we have encapsulated it into a black box. Right, now in order to understand what is happening inside this black box, we go on to the next element, that is the truth table. Also, the truth table and the Boolean expression that we will learn next will help us understand the functionality inside the MUX, and further will help us to write the code in Verilog as to how this functionality should be written in the form of a hardware description language, starting from the block diagram that we have just seen for the digital entity that we are trying to code. Right, so now let us begin with the truth table and understand the functionality of the MUX. So for 2:1 MUX, that is the simplest of all the MUXes, we have 0 as the enable. That means when enable is 0, there is no function being held in the entity, and hence whatever the value of s may be, y shall always be 0, right? Next, what we do is when enable is 1, then if s is 0, then y has to be a. This means that if s can be 0 or 1, because this is just one entity that will select a value from A or B, then A has to be 0 and B has to be 1. So that when S is 0, A becomes the value which is to be given to Y. And when S is 1, B becomes the value which has to be given to Y. That means the select value for S is 0 or 1, because this is just a 1-bit entity, and to select either of A or B, these two 1-bit entities, that is 0 and 1, are being used to get the output. Next, similarly, if we have enable 1, that means the circuit is on, and S is 1, then the output must be B. That means whatever the value of B is should be coming into Y. Another small thing that I would like to add here is that here I have defined the functionality that if enable is 0, that means the circuit is switched off, and whatever the value of S may be, the value of Y has to be 0. But here you can either keep a cross, that means the value of Y is not defined, or any other fixed value that you can put in this condition when enable is switched off, right? Now let us move on to the next part of the multiplexer, and that is the Boolean equation. So for a Boolean equation which can be derived from the truth table, here we can see that Y, which is the output, can get the value enable being 1. This means that only when enable is 1 shall this functionality of the circuit work. Now this functionality, as you can see from the truth table, it says that if S bar is there, then A will be the output, or if S is there, then B shall be the output. Considering the value of S as 0, this S bar depicts 0, and A is the value that you get when S is 0. That means S bar. Also, apart from this, you get a value when S is 1, you get a value B. So this is what the Boolean expression says. Now let us move on to the uses as to whatever we've studied up till now for a multiplexer. How is a multiplexer actually used in a circuit, and why are we trying to code the multiplexer in a Verilog code, and what is its importance? Now let us look at what are the uses of multiplexer. So the first use of a multiplexer is that it helps in the reduction in number of wires, its complexity and its cost. The second use is that it helps in the implementation of various circuits using MUX. So what happens is, as you can see in the diagram, if you look back at the Boolean expression that I just taught you, you can very well see that this circuit is a replication of that MUX, right? Obviously without the enable. But this circuit also represents what was there in the black box, right? Now, similarly, what if this entire big circuit is converted into this entity of a 2:1 MUX, right? So, as you can see, this helps in reducing the number of wires, the complexity and the cost of the circuit. Because every time repeating these selectivity functions all across the digital circuit would be very difficult to attain. And to prevent that, what we do is we convert it into a MUX, and whatever selectivity functions we need to use all throughout the digital circuits, we always use a MUX to give that functionality. Secondly, this MUX design can also be used to implement various other circuits like adders, subtractors, etc. Right? So that is another way in which this helps in reducing the complexity and the cost. Not only that, it helps in building up many other circuits, not just in places where specifically selectivity is required. Now let us look at the Verilog code for a 2:1 multiplexer, that is the simplest of all the multiplexers. And while you understand the Verilog code for a 2:1 multiplexer, once you understand the technique to write it, you will very well be able to build upon this small multiplexer and understand all the other big multiplexers after this. So let us start with the easiest modeling style, and that is the data flow modeling style, and understand how to write the Verilog code for a 2:1 multiplexer. So when we start with writing the Verilog code, the first thing that should come into your mind is the diagram that we initially had seen, and followed by all the inputs and the outputs that it had. So all of these were the inputs and this was the output. Also, right now, while mentioning the inputs, outputs and the module, we do not need to know what is happening inside here, right? So all of this is in a black box and we don't need to look at it right now. Therefore, we start with the first statement of module. We mention the name of the module followed by what all inputs and outputs might be present in the code. Followed by this, what you do is you have the output as Y being mentioned and the input as A, B, S being mentioned, so that you have a distinction as to what all are inputs and what is the output. Now, in order to understand the assign statement, I have omitted here enable, and I have removed this part and just kept A, B and S as inputs and Y as the output. We shall see how to design a circuit using enable in the next method, right? So first, if we begin with the assign statement, which is how the data will flow inside this entity of ours. For that, we have Y as the output, which will get the value as B if S is true, that means if S is 1, and it will get a value of A if S is 0. So the assign statement, or the conditional assign statement to be specific, tells us whether we get the input as B or A depending upon the value of S, which could be true being S is equal to 1 and which could be false being S is equal to 0, hence depicting B and A as the outputs for the value Y. So this is the very simple example of how to use the conditional assignment statement and how to exploit the functionality of true and false in the select statement for a simple 2:1 multiplexer. Followed by this, we simply just end the module. Let us now understand the behavioral modeling style of the Verilog code for a 2:1 MUX. Now for that, let us begin straight away with the ports of the 2:1 MUX so that we can again visualize it via the block diagram that we have already studied. So we have module and the name of the module followed by all the inputs and the output ports that we have mentioned in the block diagram of a 2:1 MUX, excluding the inside black box where the functionality happens. That means that right now our only focus is at the input and output ports and completely counting all of them so that we don't miss any. And we are not really concerned about the inside functioning of the 2:1 multiplexer right now, right? So after we do this, that means we put in the input and the output explicitly differently, with the input being called the wire and the output as reg. We put in all the inputs and the outputs definitely with the enable signal here, so that we can also understand what is the importance of enable in a circuit. The enable signal helps in switching on and off a digital entity. This means that when you switch on a particular entity using enable, you can use it, and whenever there is no use of that particular entity, you can always switch it off using the enable signal, and this helps in reducing the power consumption of the circuit. Hence, we should also know how to create Verilog codes which also include enable signals. Followed by this, we have the always @ statement followed by the sensitivity list. Now, as we all know, the sensitivity list for a combinational circuit can easily be written by mentioning a star. This means that any change in the inputs will create a change in the functionality. But if we really need to look deeper into the circuit, we can see that only a change in enable or a change in select line should create a change in the output. So you can always replace this star with this so that it becomes more deeply clear to you how the multiplexer works. Followed by this, we write the begin statement, and since the behavioral modeling style in Verilog is very similar to the software programming, we always use statements like if, else, case, etc. to write down our codes. Now this part of the code here is actually the black box that we've already studied always, and this is the black box part where we need to put in the functionality. So for functionality, we will try to refer to the truth table of the 2:1 multiplexer. Here is the truth table that we can use in order to write the modeling style. And if we see from the first statement of if that if enable is 1, that means if enable is true, then we begin, and we have another if else nested statement in the previous if, and here we have if s is 1, that means if enable is 1 and s is 1, then the output should be b, else if s is 0, then the output should be a. Similarly, these two statements after being covered, we look at the third possibility where if enable is not equal to 1 and enable is false or 0, we have set the condition as y is equal to 0. And with that, we end the if else over here, and we also end the previous if else statement followed by the end module. Now let us look at the summary of the entire lecture, and let us just once see whether whatever we wanted to understand and learn at the beginning of the lecture is all that fulfilled up till now. So first we learned about the multiplexers. What are multiplexers and what are the different entities of a digital design, as in the Boolean expression, the truth table, and the block diagram that describe the digital circuit efficiently, and also it helps in giving a clarity to your mind while you write the codes for these digital circuits. Now followed by this, we have a 2:1 MUX block diagram, a truth table and a Boolean expression which we have already understood. Then we studied the uses of multiplexer, what are multiplexers and how they are used in digital circuits and how they help in reducing the complexity in a bigger circuit. Then we have studied the Verilog code of a 2:1 multiplexer, both for a data flow modeling style and a behavioral modeling style, so that we can compare and contrast as to which method we are comfortable in and what all methods or what all ways of thinking can be applied to our digital circuit with all the necessary background that we already have in order to create a Verilog code for the digital design, so that it becomes really easy for us to not only understand the digital circuit but also create very smoothly its Verilog code. Thank you so much. Let us meet very soon in the next lecture.